Hello there, and welcome to the Sleepy Wonders channel. Tonight we are drifting far beyond the familiar glow of stars and planets, beyond the comforting light of our own sun, into a place where gravity grows so deep that even light itself begins to slow down, bend, and sometimes disappear entirely. We are traveling to the edge of understanding, to the dark hearts of black holes. But tonight, we are not here to be frightened. We are here to rest, to let our minds drift into the patient silence of the cosmos, where the most extreme objects in the universe have been waiting for us with the kind of stillness that only eternity can offer. Black holes are not monsters. They are not devourers or destroyers. They are the universe's deepest mysteries. Places where matter has gathered so densely that the fabric of space and time itself has been changed forever. They are the quietest, most patient objects in existence. And tonight, we will explore them gently, piece by piece, letting their strangeness wash over us like a slow, dark tide. Let your body soften. Let your breathing slow. Let your mind settle into stillness as we begin our journey into the silent places of the cosmos. Let us begin. The story of black holes begins not with darkness, but with light. It begins with the stars, those great, glowing furnaces that fill the night sky with their patient fire. Stars are born from cold clouds of gas and dust that drift through space for millions of years. Gravity gathers these clouds into denser pockets, and as the gas collapses inward, the center grows hotter and hotter until finally, hydrogen atoms begin to fuse into helium. A star ignites. This is how our sun began. This is how every star in the night sky began. And for the vast majority of stars, this process of fusion will continue for billions of years. The star will burn steadily, converting hydrogen into helium in its core, and it will shine with a steady, dependable light. But stars are not eternal. Eventually, they run out of fuel. And when that happens, gravity takes over. In a star like our sun, the end is gentle. The star swells into a red giant, sheds its outer layers into space, and leaves behind a dense, hot core called a white dwarf. This white dwarf will cool slowly over billions of years, fading from brilliant white to dimmer shades until it becomes a quiet, dark ember. This is the fate of most stars. But some stars are much more massive than our sun. And for these giants, the ending is very different. Imagine a star so large that it has a core pressure and temperature far beyond anything our sun could ever achieve. These massive stars burn through their fuel at an astonishing rate, racing through the elements in their cores like a fire-consuming dry wood. They fuse hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. But iron is where the story changes. Iron cannot fuse to release energy. It is the ash of nuclear fusion, the end of the line. When a massive star's core becomes iron, fusion stops. And without the outward pressure of fusion to hold it up against gravity, the core collapses inward at a speed that is almost impossible to imagine. In less than a second, a core the size of Earth collapses into a sphere only a few miles across. The density becomes so extreme that protons and electrons are forced together, forming neutrons. The core becomes a neutron star, an object so dense that a single teaspoon of it would weigh billions of tons. But if the star is massive enough, if the core is more than about 3 times the mass of our sun, even neutron pressure cannot hold. The core continues collapsing, crushing matter down into a state that we simply cannot recreate in any laboratory. Gravity becomes the only force that matters, and it wins completely. What remains is a black hole. At the center of a black hole lies a singularity, a point where all the mass of the collapsed star has been compressed into zero volume. The laws of physics, as we know them, break down at the singularity. Space and time lose their familiar meaning. Density becomes infinite. And around this singularity, there is a boundary called the event horizon, the point of no return. Once anything crosses this boundary, it can never escape, not even light. This is what we mean when we say black holes are black. They do not emit light, and they reflect none. They are the absence of light in a universe filled with it. But they are also places of extraordinary power. A black hole with the mass of our sun would be only a few kilometers across, roughly the size of a small city. Yet it would contain the entire mass of our star, compressed into that tiny space. The gravity near such an object would be so intense, the time itself would slow down compared to distant clocks. This is not science fiction. This is the physics of gravity as Einstein described it in his theory of general relativity. Gravity does not merely pull on objects, it pulls on time itself. Near a black hole, gravity is so extreme that time passes more slowly than it does for someone far away. If you could hover near the event horizon of a black hole for what felt like a few minutes, years might pass back on Earth. The universe outside would race ahead while you remained almost still. To you, however, everything would feel completely normal. Your watch would tick at the same pace as always. Your heart would beat in its usual rhythm. But to someone far away, you would appear frozen in time, growing redder and dimmer as you faded from view. This strange split in time reveals something essential about the universe. Time is not a universal rhythm shared everywhere at once. It can bend with gravity, stretch with motion, and behave differently depending on where you are. Near a black hole, this effect becomes extreme. To a distant observer, something falling toward the event horizon seems to slow down, then freeze, then slowly fade to red and vanish. For the falling object itself, however, time continues normally. The person falling in would not even notice the exact moment they crossed the horizon. They would simply drift through it, still seeing stars, still feeling gravity, just no longer able to send any signal back out. This is one of the most humbling ideas in physics. Time is not a fixed backdrop against which events unfold. It is woven into the fabric of space itself, and that fabric can be stretched, bent, and warped by mass and energy. Black holes are where this bending becomes so extreme that the fabric tears. The event horizon is not a physical wall, not a surface you would crash into. It is a mathematical boundary, a threshold where the equations of gravity change their meaning. Once you cross it, the direction of time itself seems to change. The future points inward. The center of the black hole is no longer a place you can reach. It is a time you will inevitably encounter. And yet, black holes are not reaching for us. They are not waiting to consume us. They are distant, patient, and still. They have been there longer than life on Earth, and they will remain long after everything we know has changed. There is something peaceful in that patient stillness, something that invites us to rest. Black holes come in different sizes. The smallest are called stellar mass black holes, and they form from the collapse of massive stars, as we have just described. These black holes typically weigh between about 3 and a few dozen times the mass of our sun. They are scattered throughout galaxies, remnants of stars that once blazed with incredible brilliance. But there are also much larger black holes. millions or even billions of times the mass of our sun. These are called supermassive black holes, and they sit at the centers of almost every large galaxy, including our own Milky Way. How do supermassive black holes form? This is one of the great questions in astrophysics. They are too large to have formed from a single star. Some scientists believe they grow by merging with other black holes, absorbing them over billions of years. Others think they may have formed from the direct collapse of massive gas clouds in the early universe, skipping the star stage entirely. Still others suggest that they started as smaller black holes in dense star clusters and grew by swallowing stars, gas, and even each other. The details are still being debated, but the evidence for their existence is overwhelming. At the center of our own galaxy lies a supermassive black hole called Sagittarius A. It contains about 4 million times the mass of our Sun, compressed into a region roughly the size of the orbit of Mercury. We cannot see this black hole directly because it emits no light, but we can see its influence on nearby stars. Astronomers have tracked the orbits of stars around Sagittarius A for decades, watching them swing around the invisible center at extraordinary speeds. Some stars complete their orbits in just a few years, traveling at thousands of miles per hour. These orbits reveal the presence of a massive object, a huge amount of mass packed into a tiny region. The only thing that fits the evidence is a black hole. This is what science looks like when you cannot see your subject directly. You observe its effects. You watch how it pulls on everything around it. You measure the orbits, the speeds, the radiation, and you build a picture of something that is otherwise invisible. And the picture is always the same. Something deep, dark, and immensely heavy at the center of things. And yet, Sagittarius A is quiet by cosmic standards. It is not actively feeding on large amounts of material. It does not blaze like a quasar. It simply sits at the heart of our galaxy, patient and still, influencing the motion of billions of stars while emitting only the faintest whispers of radiation. Our galaxy has a quiet heart, and that quietness is part of what makes it safe for us. Many people worry that black holes could swallow the Earth. This is understandable when something is described as a region where nothing can escape. It sounds threatening. But black holes do not hunt. They do not wander through space looking for things to consume. They simply exist where they are, and objects must get very close to them in order to be captured. If our Sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now. The gravitational pull at our distance would be unchanged. We would be cold, of course, because we would lose sunlight. But we would not be pulled in. From far enough away, a black hole behaves exactly like any other object of the same mass. The danger comes from getting too close. If Earth were pushed closer to a black hole, much closer, then the gravitational gradient would become extreme. The side of Earth facing the black hole would feel a much stronger pull than the side facing away. This difference in force, called tidal gravity, would stretch and distort the planet. It would tear it apart. But this only happens very close to the event horizon. At a safe distance, the black hole's gravity is just gravity. This is an important distinction. Black holes are not cosmic vacuum cleaners. They do not suck everything in from great distances. They are more like heavy weights on a trampoline. They bend the fabric of space around them, and anything that rolls too close will fall in. But far away, the curvature is gentle, and objects can orbit safely for billions of years. There is something deeply peaceful in this understanding. The universe is not chaotic or dangerous. It is orderly and predictable. Gravity works the same everywhere. Whether it is the gentle tug of the moon on our oceans or the immense pull of a supermassive black hole at the center of a galaxy, the same laws apply. The same mathematics governs both the small and the large. And in that consistency, there is comfort. Black holes also challenge our most basic assumptions about space and time. Consider the event horizon again. At this boundary, gravity becomes so strong that the escape velocity exceeds the speed of light. This means that even light, the fastest thing in the universe, cannot get out. But what does that look like from the outside? Imagine someone falling into a black hole. To a distant observer, the falling person would appear to slow down as they approach the horizon. Their image would become redder as the light stretched. They would seem to freeze at the edge, never quite crossing. And then they would fade, becoming dimmer and dimmer until they disappeared entirely. But for the person falling in, everything would be different. They would see the outside universe speed up as they approached the horizon. The stars would shift and blur. The black hole's shadow would grow larger in their field of view. And then, without any clear boundary, they would pass through the event horizon and into the interior. There is no dramatic moment, no flash of light, no sudden change. Just a gentle drift into the darkness. What happens after crossing the horizon is one of the great mysteries of physics. Our equations suggest that the singularity, the point of infinite density, is inevitable. But we do not know what form that singularity takes. Some physicists believe that the singularity is real, that space and time literally come to an end there. Others think that our equations are incomplete, that a deeper theory of quantum gravity would smooth out the singularity and replace it with something else. The truth is, we do not know. And that is part of the beauty of black holes. They hold secrets that may never be fully revealed. And yet, black holes are not silent. They do not simply sit in the dark, completely cut off from the universe. Around them, matter can form what is called an accretion disk, a swirling disk of gas and dust that spirals inward toward the event horizon. As this material falls in, it accelerates and heats up, releasing enormous amounts of energy. The region around a black hole can become incredibly bright, far brighter than the galaxy that hosts it. These are called active galactic nuclei, and they are among the most luminous objects in the universe. When a supermassive black hole is actively feeding, it can produce jets of matter that shoot outward at nearly the speed of light. These jets are powered by the rotation of the black hole and the magnetic fields generated by the accretion disk. They can extend for hundreds of thousands of light years, far beyond the boundaries of the galaxy itself. The energy they carry is staggering, enough to reshape entire galaxies, to heat gas, to prevent star formation, and to change the environment of the cosmos on the largest scales. This is a black hole in action, not a devourer, but an engine. A converter of mass into energy with an efficiency far beyond anything we can imagine. The power of a quasar, an active black hole, can outshine the combined light of every star in its galaxy. And yet, the black hole itself remains invisible, hidden behind the glowing material around it. The darkness is surrounded by brilliance. Some black holes are even larger than Sagittarius A, much larger. The most massive black holes known contain tens of billions of solar masses. One of the largest, known as TON 618, is estimated to have a mass of about 6 billion suns. Its event horizon would be so large that it could span the entire orbit of our solar system many times over. If you could stand at the center of such a black hole, you would see a horizon stretching across the sky in every direction. The scale is almost impossible to grasp. And yet, these giants are not monsters either. They are ancient, stable, and patient. They formed in the early universe, feeding on gas and merging with other black holes to become the enormous objects they are today. They sit at the hearts of their galaxies, influencing everything around them without ever revealing themselves directly. They are the hidden rulers of the cosmos. There is something humbling about this. Our galaxy, the Milky Way, contains billions of stars, spread across a disk 100,000 light-years wide. And at its center, holding it all together, is a black hole that we cannot see. The same is true for almost every large galaxy in the universe. The darkness runs deep, but black holes are not only found at the centers of galaxies. There are stellar mass black holes scattered throughout the Milky Way, remnants of massive stars that ended their lives in collapse. Some of these black holes are in binary systems, orbiting with a companion star. In these systems, the black hole may pull material from its companion, creating an accretion disk and emitting X-rays that we can detect from Earth. These X-ray binaries are how we discovered many of the stellar mass black holes we know today. The first black hole ever discovered was Cygnus X1, found in 1964. It is located about 6,000 light-years from Earth, in the constellation Cygnus. Cygnus X1 is a binary system, a black hole orbiting a massive blue star. The black hole pulls gas from its companion, and that gas heats up as it spirals inward, producing X-rays that can be detected by satellites. The mass of the black hole is about 14 times the mass of our Sun, making it a textbook example of a stellar mass black hole. The discovery of Cygnus X1 was a turning point in astrophysics. It confirmed that black holes are not just theoretical predictions, they are real objects that exist in our galaxy. Since then, we have found dozens of stellar mass black holes, and we know that there must be millions more in the Milky Way alone, quietly drifting through space, unseen and unknown. Some of these black holes are solitary, moving through the galaxy without any companion to reveal their presence. These isolated black holes are invisible to us, except when they happen to pass in front of a distant star and produce a brief brightening through gravitational microlensing. This effect occurs because the black hole's gravity bends and magnifies the light of the star behind it, acting like a lens in space. It is a subtle signal, but it can reveal the presence of otherwise invisible objects. The existence of these solitary black holes raises an interesting possibility. If there are millions of black holes in our galaxy, some of them must be relatively close to us. Perhaps the nearest black hole is only a few dozen light-years away. Perhaps it is already known, hiding in the data of some survey, waiting to be recognized. The night sky is filled with secrets that we are only beginning to uncover. And yet, even the nearest black hole would be harmless to us. It would simply be there, orbiting the center of the galaxy like everything else, its gravity no more threatening than that of a distant star. We could go about our lives, never knowing it was there and it would never disturb us. The universe is vast, and we are safely tucked away in a quiet corner of it. Black holes are also linked to one of the most profound discoveries of the past century: gravitational waves. In 1916, Albert Einstein predicted that massive objects accelerating through space would create ripples in the fabric of space-time, tiny disturbances that travel outward at the speed of light. These ripples are called gravitational waves, and they are produced by some of the most violent events in the universe. Colliding black holes, merging neutron stars, and supernova explosions. For decades, gravitational waves remained undetected. They are incredibly weak. Even the most powerful events in the cosmos produce ripples that are only a fraction of the width of an atom by the time they reach Earth. But in 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made history by detecting gravitational waves for the first time. The signal came from two black holes, each about 30 times the mass of our Sun, spiraling together and merging into a single, larger black hole. The event had occurred more than 1 billion years ago, in a distant galaxy far beyond our own. The black holes had orbited each other, growing closer and faster, until their orbital speed approached the speed of light. At that moment, they merged, releasing an enormous burst of gravitational energy. 3 times the mass of our Sun, converted entirely into ripples in space-time. That energy traveled through the cosmos for over 1 billion years, crossing countless galaxies and stretches of empty space, before finally reaching Earth and causing LIGO's detectors to tremble by an almost imperceptible amount. The detection was a triumph of human ingenuity. It confirmed a major prediction of Einstein's theory and opened a completely new way of observing the universe. Instead of collecting light, we can now detect the vibrations of space-time itself. It is like gaining a new sense for cosmic events that might otherwise remain hidden. And since that first detection, LIGO and other gravitational wave observatories have detected dozens of black hole mergers, neutron star collisions, and other events. Each detection adds to our understanding of black holes. We now know that black holes can merge, forming even larger black holes in the process. We know that these mergers are common, happening throughout the universe on a regular basis. We know that the black holes involved in these mergers come in different sizes, from a few solar masses to several dozen solar masses. And we are beginning to see the patterns that govern their formation and evolution. The sound of a gravitational wave is a chirp, a rising tone that starts low and gets higher as the black holes spiral faster and faster. Then it stops abruptly when the merger is complete. In that brief signal, lasting only a fraction of a second, there is an entire story. The final moments of 2 black holes, their long dance ending in a single, more massive object. The silence that follows is deafening. For the first time, humans have not just seen the universe. We have heard its deep structure move. And what we have heard is the sound of darkness itself. Black holes also reveal themselves through the way they bend light. Because they warp the fabric of space, they can act as lenses, magnifying and distorting the images of objects behind them. This is called gravitational lensing, and it is one of the most powerful tools in astronomy. When a black hole passes in front of a distant galaxy, its gravity bends the light from that galaxy, creating arcs, rings, and multiple images. By studying these distortions, astronomers can measure the mass of the black hole and learn about the distribution of matter in the universe. In some cases, gravitational lensing has revealed entire populations of black holes that would otherwise be invisible. It has also been used to detect dark matter, the mysterious, invisible substance that makes up most of the mass of the universe. Dark matter does not emit or absorb light, but it does exert gravity, and gravitational lensing is one of the best ways to map its distribution. The black holes we see are only the visible edge of a much deeper and stranger reality. The event horizon of a black hole also has interesting properties. It is often thought of as a one-way membrane. Things can go in, but nothing can come out. But in the 1970s, the physicist Stephen Hawking made a remarkable discovery. He found that black holes are not completely black. They emit a faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation is incredibly weak for large black holes, far too faint to detect with current technology. But it has profound implications. Hawking radiation suggests that black holes slowly lose mass over time. A black hole that is not feeding on new material will gradually evaporate, shrinking until it eventually disappears. For a stellar mass black hole, this process would take much longer than the current age of the universe, about 10^67 years, a number so vast that it has no meaning in human terms. But for very small black holes, the evaporation would be faster. A black hole with the mass of a mountain would evaporate in a fraction of a second, releasing an enormous burst of energy in the process. This idea that black holes could evaporate linked gravity, quantum mechanics, and thermodynamics in a deep and unexpected way. It suggested that black holes have entropy or disorder, and that they obey laws similar to those of ordinary physical systems. The study of black hole thermodynamics has become one of the most active areas of theoretical physics, and it may ultimately lead to a deeper understanding of the fundamental nature of reality. For now, however, black holes remain deeply mysterious. We know they exist. We know how they form. We know some of their properties. But the singularity at the center, the nature of the event horizon, the resolution of the quantum information paradox, these are open questions that may take decades or centuries to answer. The darkness holds its secrets close, but that is part of the comfort of black holes. They remind us that the universe is not fully understood, and that there is still room for wonder. The mystery is not a problem to be solved. It is a space to rest in, a place where the mind can drift, unburdened by the need for answers. There is also something deeply poetic about black holes. They are the endpoints of massive stars, the last, quiet remnants of brightness that once dominated the sky. A star that burned for millions of years, that created the elements that make up planets, oceans, and living things, eventually becomes a black hole, a silent, dense memory of all it once was. It no longer shines, but its influence remains. It shapes the motion of everything around it, holding galaxies together, bending light, stretching time. In a sense, black holes are the ultimate recyclers. They take the mass of stars and compress it into the most efficient form possible. The energy they release when they feed can rival the output of entire galaxies. And when they evaporate, over time scales longer than the age of the universe, they return that mass to the cosmos as radiation. Nothing is lost. Everything is transformed. This is a comforting thought. The universe is not a place of endings. It is a place of change. Stars become black holes. Black holes become radiation. Radiation becomes new stars. The cycle is endless, patient, and beautiful. And we are part of it, whether we realize it or not. The atoms in our bodies were forged inside ancient stars. The calcium in our bones, the iron in our blood, the oxygen we breathe. These elements were created in the hearts of stars that lived and died long before Earth existed. Some of those stars may have become black holes. Some of those black holes may still exist, drifting through the galaxy, carrying the memory of those long-gone suns. We are made of stardust, but we are also made of something older. We are made of the remnants of stars that ended their lives in the most extreme way imaginable. In a very real sense, we are the children of black holes, and yet we are also separate from them. We live in a warm, protected world, bathed in sunlight, surrounded by air and water and life. The black holes are far away, patient and still, holding their secrets in the deepest darkness. We are safe. We are comfortable. We are here together, drifting gently toward sleep. The galaxy is vast. The universe is older than we can comprehend. And at the center of it all, in the darkest places, the black holes are waiting, not to harm us, but to remind us of the scale of existence. We are small, but we are a part of something immense, and that is the comfort of it. Let us continue our journey. Let us drift deeper into the silence. There is more to discover, and no need to hurry. There is a concept in black hole physics called the photon sphere. This is a region outside the event horizon where gravity is so strong that light itself can orbit the black hole. The photons, particles of light, are caught in a kind of orbit, circling the black hole again and again without falling in or escaping. This is a delicate balance, an unstable orbit where any disturbance will send the light either inward or outward. But for a brief, eternal moment, light can circle the darkness. If you could stand near a black hole and look toward the photon sphere, you would see strange things. The light from behind the black hole would be bent around it, creating distorted images of the stars and galaxies beyond. You would see multiple versions of the same object, stretched and twisted by the intense gravity. The black hole's shadow, the event horizon itself, would appear as a dark circle against the glowing background of the accretion disk. This is what the Event Horizon Telescope captured in 2019 when it produced the first direct image of a black hole. That image, a fuzzy orange ring surrounding a dark center, was the culmination of years of effort by an international team of scientists. It was the first time we had ever seen the shadow of a black hole. The black hole in question is in the galaxy Messier 87, about 55 million light-years from Earth. It has a mass of about 6.5 billion suns. The ring of light around it is the glow of the accretion disk, and the dark circle in the center is the event horizon. Looking at that image, one cannot help but feel a sense of awe. This is an object so massive that it bends the light around it. It is the most extreme thing we have ever observed. And yet, it is also one of the most simple. A black hole has no features, no texture, no surface. It is defined entirely by its mass, spin, and charge. The event horizon is smooth and featureless. The singularity is hidden. The black hole is, in a sense, the ultimate minimal object. And yet, the simple black hole is also the most profound. It is a place where the laws of physics are pushed to their limits. It is a laboratory for testing gravity, quantum mechanics, and the nature of time. It is a window into the deepest, most fundamental aspects of reality. The more we study black holes, the more we realize how much there is to learn. One of the most fascinating questions about black holes is what happens at the center. The singularity is a point of infinite density, where the usual rules of physics break down. It is not a place in space. It is a place where space and time themselves cease to have meaning. The singularity is not a thing. It is an edge, a boundary beyond which we cannot see. Some physicists believe that the singularity is real, that it is an actual endpoint of space and time. Others think that our equations are incomplete, that a deeper theory of quantum gravity would replace the singularity with something else. One possibility is that the singularity is not a point, but a ring. A rotating black hole creates a ring-shaped singularity. Another possibility is that the singularity is a kind of wormhole, a bridge to another part of the universe or another universe entirely. These ideas are speculative, but they are grounded in mathematics. Black holes may be windows, not walls. They may be portals to other places, other times, other realities. But even if they are not, even if the singularity is the end of the line, there is something beautiful about that too. The universe has edges. There are places we cannot go. There are mysteries we cannot solve. And that is okay. The unknown is not a threat. It is a space for wonder. Black holes are often described as traps, but they are also very patient. They do not rush. They do not demand. They simply exist, waiting for whatever comes their way. And when something does come, a star, a planet, a cloud of gas, they accept it without ceremony, adding its mass to their own, growing slightly larger, slightly more massive. They are like ancient collectors, accumulating matter over billions of years, their hunger never quite satisfied. This is why supermassive black holes grow so large. They sit at the centers of galaxies, surrounded by a constant supply of gas and stars. Over time, they feed on whatever drifts too close. They grow slowly, steadily, inevitably. And as they grow, their influence expands. They shape the galaxy around them, affecting star formation, heating gas, and even influencing the orbits of stars far from the center. In a very real sense, the black hole is the heart of the galaxy, the organ that pumps energy into the system and regulates its function. The relationship between a galaxy and its central black hole is one of the most fascinating subjects in astrophysics. Observations have shown that the mass of a supermassive black hole is closely related to the mass of the bulge of its host galaxy, the dense central region where stars are packed most tightly. This relationship suggests that the black hole and the galaxy grow together, influencing each other's evolution. The black hole feeds on the galaxy, and the galaxy is shaped by the black hole. In some cases, the black hole can slow down star formation in its galaxy by blowing gas away with its jets. The energy from the black hole heats the interstellar medium, preventing gas from collapsing into new stars. In other cases, the black hole's activity may trigger star formation by compressing gas clouds. The net effect depends on the details of the system, but the black hole is always an active participant in the life of its galaxy. This is a profound shift in our understanding of the universe. We used to think of galaxies as simple collections of stars held together by gravity. Now we know that they are complex ecosystems, where the central black hole plays a starring role. The darkness at the center is not a passive observer. It is a force that shapes the cosmos. And yet, the black hole itself remains hidden. We can see its effects, but we cannot see it directly. The event horizon is the boundary between what we can know and what we cannot. Beyond that boundary, there is no light, no information, no way to send a signal back to us. The black hole is the ultimate secret keeper. This is why black holes capture our imagination. They represent the limits of knowledge, the edge of the known universe. They are places where reality, as we understand it, breaks down. They are the most extreme objects in the cosmos, and they are also the most mysterious. They are darkness made visible, the absence of light in a universe that is defined by light. There is comfort in that mystery. There is relief in knowing that we do not need to understand everything. The universe is vast and strange, and we are small. We are part of a story that is much larger than ourselves. We are drifting through time and space, held by gravity, guided by the same laws that govern the black holes themselves. We are connected to them, not separate from them. When you look up at the night sky, you are looking into the past. The light from distant stars has traveled for years, decades, centuries, or even millennia to reach your eyes. Some of those stars may be gone now, their light still traveling through space, carrying the memory of their brightness. Some of those stars may have become black holes, their light extinguished, their mass hidden in the dark. But even though we cannot see black holes, we can feel their presence. Their gravity reaches across space, influencing the motion of stars and gas and planets. They are the invisible architects of the cosmos, shaping the structure of galaxies, clusters, and the universe itself. They are the hidden rulers of the night. And they are patient, so patient. They have been here since the dawn of time. They will be here long after we are gone. They will outlast the stars. They will outlast the galaxies. They will outlast everything we know. In the far future, when the universe is dark and cold, black holes will still be there, slowly evaporating, slowly releasing their mass back into the void. There is a strange peace in that thought. The black holes are eternal, in a sense. They are the last objects to fade in the universe. They are the final echoes of the stars that once lit up the cosmos. They are the end of the story, and they are also the beginning of something else. When they evaporate, they return their mass to the universe's radiation, which may one day form new stars, new planets, new life. The cycle continues. The universe is not static. It is constantly changing, evolving, transforming. Black holes are part of that transformation. They are the agents of change, the catalysts that turn stars into radiation, matter into energy. They are the great converters, the engines of the cosmos. We are part of that cycle too. We are made of atoms that were once inside stars, and those stars may have become black holes. We are connected to the most extreme objects in the universe. We are not separate from them. We are part of them, and they are part of us. Tonight, as we drift towards sleep, we can let our minds rest in the knowledge that we are part of something immense. We are part of the universe, and the universe is part of us. The black holes are not our enemies. They are our relatives, our ancestors, our future. They are the dark heart of the cosmos, and they are beautiful. Let us rest in that beauty. Let us drift into the patient dark. There is nothing to fear. There is only the quiet hum of the universe, and the gentle pull of gravity, and the soft, endless night. There is a type of black hole that is even stranger than the ones we have discussed so far. They are called primordial black holes, and they may have formed in the first moments after the Big Bang, before stars and galaxies existed. In the extreme conditions of the early universe, regions of space could have collapsed directly into black holes without ever becoming stars. These primordial black holes could be very small, some with the mass of a mountain or even less. Others could be as massive as a star or more. Primordial black holes are still theoretical. We have not yet observed one definitively. But if they exist, they would be fascinating objects. A black hole with the mass of a mountain would be only the size of an atom. It would be the densest object imaginable, and it would radiate Hawking radiation much faster than a larger black hole. Some primordial black holes would have already evaporated by now, releasing their mass as radiation in the early universe. Others would still be around, their tiny forms drifting through the cosmos, invisible and silent. The existence of primordial black holes could also explain some of the mysteries of the universe. Some physicists have suggested that they could be the source of dark matter, the invisible substance that makes up most of the massive galaxies. If there are enough primordial black holes scattered throughout the universe, their gravity could account for the missing mass that we attribute to dark matter. This is a speculative idea, but it is not impossible. Primordial black holes also raise interesting questions about the very early universe. What was it like in those first moments, when the universe was denser and hotter than anything we can imagine? How did the first structures form? What was the nature of reality at that time? These are deep questions, and they may remain unanswered for a long time. But the possibility that black holes were there from the very beginning is a humbling thought. The universe began with an event called the Big Bang, not an explosion inside an empty room, but an expansion of space itself. The universe was incredibly hot and dense, and it has been cooling and expanding ever since. In those first moments, the conditions were so extreme that the laws of physics, as we know them, may not have applied. Quantum effects dominated, and the distinction between matter and energy was blurry. It was a time of enormous energy, enormous potential, and enormous mystery. If primordial black holes formed during that time, they would have been shaped by forces we do not fully understand. They could carry information about the early universe that is otherwise inaccessible to us. They could be fossils of a time before stars, before galaxies, before the cosmos took its current form. They could be windows into the birth of existence itself. This is one of the most exciting possibilities in modern physics. Black holes may be the key to understanding the early universe. They may be the link between the quantum world and the cosmic world. They may reveal the nature of gravity, the nature of time, and the ultimate structure of reality. The more we study them, the more we realize how much they have to teach us. But for tonight, we do not need to solve those mysteries. We can simply rest in the wonder of them. The black holes are there, holding their secrets, patient and eternal. We are here, drifting toward sleep, our minds free to wander through the darkness. There is no urgency. There is no need to understand everything right now. There is only the soft rhythm of our breathing and the quiet whisper of the cosmos. Let us continue our gentle journey. There is more to explore, and the night is long. The gravity of a black hole is so intense that it can create what is called a gravitational wave, a ripple in the fabric of space-time that travels outward at the speed of light. Gravitational waves are produced whenever massive objects accelerate, but the strongest waves come from the most extreme events. Merging black holes, colliding neutron stars, and supernova explosions. The discovery of gravitational waves has revolutionized astrophysics. It has given us a new sense, a new way of observing the universe. Instead of collecting light, we can now detect the vibrations of space-time itself. It is like hearing for the first time after a lifetime of silence. The universe is not quiet. It is humming with the echoes of its most dramatic events. Each gravitational wave detection tells a story. When two black holes merge, the wave signal is a chirp, a rising tone that gets higher as the black holes spiral faster and faster. At the moment of merger, the signal peaks and then drops off sharply. The chirp is the sound of two black holes becoming one. It is the sound of the most violent event in the universe, compressed into a fraction of a second. And yet, for all their violence, black hole mergers are also incredibly clean. The black holes do not leave behind any debris, no gas, no dust, no stars. They simply merge into a single larger black hole, releasing a huge amount of gravitational energy in the process. The final black hole is perfectly spherical, defined only by its mass, spin, and charge. It is the ultimate expression of simplicity. The first gravitational wave detection in 2015 was from a merger of two black holes with masses of 29 and 36 times the mass of the Sun. They merged to form a black hole of about 62 solar masses, releasing 3 solar masses worth of gravitational energy in the process. That energy was equal to the total energy output of the entire visible universe over a few seconds. The event happened 1.3 billion years ago, and the ripples traveled across the cosmos to reach Earth at the exact moment LIGO was ready to detect them. The precision of this detection is astonishing. LIGO uses lasers and mirrors to measure distances with incredible accuracy, down to a fraction of the width of a proton. When a gravitational wave passes through the detector, it stretches space in one direction and squeezes it in another, changing the distance between the mirrors by a tiny amount. The fact that we can measure such tiny changes is a testament to human ingenuity and persistence. Since that first detection, LIGO and its partners have detected dozens of black hole mergers and neutron-star collisions. Each detection adds to our understanding of black holes. We now know that black holes of different sizes can merge, forming even larger black holes. We know that these mergers are common in the universe, happening several times per year in the volume of space that LIGO can observe. We know that black holes can spin, and that their spin affects the gravitational wave signal. We are learning more every day. The gravitational wave sky is opening up before us, revealing a universe that was previously invisible. It is a new era of astronomy, and black holes are at the center of it. But gravitational waves are not the only way black holes reveal themselves. They also bend light, as we have seen, and they emit X-rays when they feed on matter. Each of these methods gives us a different view of black holes, a different piece of the puzzle, and when we combine them, we begin to see the full picture. The picture is still incomplete. There are many things we do not know about black holes, but the progress we have made in the last few decades is remarkable. We have gone from wondering whether black holes exist to studying them in detail. We have taken a picture of a black hole. We have heard the sound of black holes merging. We have mapped their distribution in the universe. The darkness is slowly becoming a little less dark, and yet, black holes remain mysterious. The singularity at the center is still a puzzle. The nature of the event horizon is still debated. The information paradox, the question of what happens to information that falls into a black hole, is still unresolved. These are deep questions, and they may require a new theory of physics to answer. But the questions themselves are beautiful. They remind us that the universe is not fully understood. They remind us that there is still room for wonder. They give us something to explore, something to dream about, something to drift toward as we fall asleep. Black holes are not just objects in the universe. They are ideas. They are symbols. They represent the unknown, the mysterious, the edge of understanding. They are a reminder that the universe is larger than our imagination. They are a reminder that there is always more to discover, more to learn, more to explore. And that is part of the comfort of black holes. They are not a wall. They are a door. They are not an end. They are a beginning. They are the frontier of human knowledge. And they invite us to keep looking, keep wondering, keep dreaming. Let us rest in that wonder tonight. Let us drift into the darkness, knowing that it is not empty. It is full of mystery, full of possibility, full of the quiet hum of the universe. The black holes are there, patient and still, holding their secrets in the deepest darkness. And we are here, safe and warm, drifting gently towards sleep. There's nothing to fear. There's only the dark, and the stars, and the silence. And the silence is golden. Part 2. And so we continue. The black holes are still there, patient and still, and we are still drifting. The night is long, and the universe is vast. There is no rush. As we go deeper into the subject, we encounter one of the most extraordinary ideas in modern astrophysics: the concept of the black hole information paradox. This paradox arises from a conflict between two pillars of modern physics: general relativity, which governs gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles at the smallest scales. The paradox is about what happens to information when it falls into a black hole. In classical physics, the physics of everyday objects, information is never lost. If you burn a book, the information in it is not destroyed. It is transformed into heat, light, and ash. In principle, if you could measure every particle of the ash, the smoke, and the radiation, you could reconstruct the original book. The information is still there, just in a different form. In quantum mechanics, this principle is even stronger. Quantum information is conserved. It cannot be created or destroyed. It can change form, but it cannot disappear. This is a fundamental law of nature, and it is one of the most well-tested principles in physics. But black holes seem to violate this law. According to general relativity, anything that falls into a black hole, including the information that describes it, is lost forever. It crosses the event horizon, reaches the singularity, and disappears from the observable universe. The information is gone. And if black holes evaporate through Hawking radiation, the radiation that comes out is thermal, featureless, and random, carrying no information about what fell in. The information appears to be destroyed. This is the information paradox. If information is really destroyed, then quantum mechanics is wrong. But if quantum mechanics is right, then somehow the information must escape. The problem is that general relativity and quantum mechanics are two of the most successful theories in the history of science, and they disagree about what happens at the event horizon of a black hole. This paradox has occupied the minds of the world's greatest physicists for decades. Various solutions have been proposed. Some suggest that the information is encoded in the Hawking radiation in a subtle, non-local way. Others propose that the information is stored in a firewall at the event horizon, a region of intense energy that destroys anything that falls in. Still others suggest that the black hole is not a one-way street, but a bridge to another universe, a wormhole that carries information somewhere else. The resolution of the information paradox may require a new theory of physics, one that unites gravity and quantum mechanics. This is the quest for quantum gravity, one of the greatest challenges in modern science. It is a search for a theory that describes the universe at its most fundamental level, where the distinction between space and time breaks down, and where the quantum nature of gravity is revealed. Black holes are the key to this quest. They are the bridge between the very large, the cosmos, and the very small, the quantum world. They are where the two domains meet, and where the conflicts between them are most severe. By studying black holes, we may be able to uncover the deepest secrets of nature. But this is a long journey, and for tonight, we do not need to solve it. We can rest in the mystery. We can let the paradox be a puzzle for another day. Tonight, we are here to rest. The event horizon itself is a fascinating concept. It is not a physical barrier, but a mathematical boundary, the surface beyond which nothing can escape. But what does the event horizon look like? If you could approach a black hole, you would not see a dark sphere hovering in space. You would see something stranger. Because gravity bends light, the black hole's event horizon would appear to cover more than half of the sky. The distortion of light would create a kind of optical illusion, making the black hole look larger than it really is. The stars behind it would be warped into a ring of light known as an Einstein ring. The black hole would look like a dark circle surrounded by a glowing halo. This is what the Event Horizon Telescope captured in its historic image. The image showed a bright ring of light around a dark center, the shadow of the event horizon. The ring was not the event horizon itself, but the glow of the accretion disk, warped by gravity into a circle. The dark center was the silhouette of the black hole against the bright background. It was a picture of the impossible made real. The image was the result of years of work by an international team of scientists. They used a network of radio telescopes around the world, combining their data to create a virtual telescope the size of Earth. This technique, called Very Long Baseline Interferometry, allows astronomers to see details that would otherwise be impossible to resolve. The resulting image of the black hole in Messier 87 was one of the most significant scientific achievements of the 21st century. But even more impressive than the image was the confirmation of Einstein's theory of general relativity. The shape and size of the shadow matched the predictions of general relativity with remarkable accuracy. This was a powerful test of the theory, and it passed with flying colors. The universe is strange, but it is also predictable. The same laws that govern the motion of planets around the sun also govern the shadow of a black hole 55 million light-years away. This consistency is one of the most beautiful things about physics. The universe is not chaotic. It is governed by laws that we can discover, understand, and test. The more we learn, the more we see the elegance and simplicity of nature. Black holes are extreme, but they are also simple. They are defined by just three properties: mass, spin, and charge. Everything else is stripped away. They are the Platonic ideals of physics, perfect spheres of pure gravity. This simplicity is also a source of comfort. Black holes are not capricious or unpredictable. They are governed by the same laws as everything else. They are part of the order of the universe. They are not chaos. They are structure. They are not destruction. They are transformation. And yet, black holes are also the most extreme objects in the cosmos. They push the laws of physics to their limits. They challenge our understanding of space, time, and reality. They are the ultimate frontier of human knowledge. There is also the concept of black hole spin. Black holes can rotate, and when they do, they drag space-time around with them. This effect, called frame dragging, means that anything near the black hole is forced to orbit in the same direction as the black hole's spin. The region around the black hole is not passive. It is an active, dynamic environment shaped by the black hole's rotation. The spin of a black hole is determined by the angular momentum of the star or matter that formed it. When a massive star collapses into a black hole, it retains its rotation. As the star shrinks, its rotation speeds up, like a figure skater pulling in their arms. The resulting black hole can spin at a significant fraction of the speed of light. And this spin affects everything around it. A spinning black hole can have a different shape than a non-spinning black hole. The event horizon is still spherical, but the region around it, the ergosphere, is distorted. The ergosphere is a region outside the event horizon, where space-time is dragged so strongly that objects cannot remain stationary. They must move in the direction of the black hole's rotation, even if they are not falling in. This is the energy extraction mechanism proposed by Roger Penrose, which suggests that energy can be extracted from a spinning black hole. This is a fascinating idea. A black hole can be a source of energy, not just a sink. By lowering an object into the ergosphere and then releasing it, one can extract energy from the black hole's rotation. The object would come out with more energy than it went in, having gained energy from the black hole's spin. This is theoretical, but it is consistent with the laws of physics. Black holes are not just destroyers. They are also creators. They release energy in the form of radiation, jets, and gravitational waves. They drive the activity of quasars and active galactic nuclei. They shape the evolution of galaxies. They are engines of cosmic change. This duality is part of what makes black holes so fascinating. They are dark and light, destructive and creative, simple and complex. They are contradictions wrapped in gravity. They are the ultimate paradox. And yet, black holes are also peaceful. Despite the violence of their formation and their feeding, they are, in the end, the most stable objects in the universe. A black hole at rest is a perfect sphere, unchanging, eternal. It is the closest thing to a point of stillness in a universe that is always in motion. Let us rest in that stillness. Let us imagine the event horizon as a boundary not of violence, but of peace. Beyond it, there is no light, no sound, no movement, only the deep, quiet presence of mass. The singularity at the center is not a place of terror, but of mystery. It is the end of physics as we know it, but also the beginning of something else. It is the edge of human knowledge, and that edge is beautiful. As we continue to drift, let us consider the black holes that are closest to us. The nearest known black hole is likely within a few thousand light years of Earth. It is not threatening. It is simply there, part of the fabric of the galaxy. There are probably millions of black holes in the Milky Way, scattered throughout the disk and the halo. Most of them are isolated, invisible, and silent. They orbit the center of the galaxy like everything else, their gravity blending with that of stars, gas, and dark matter. Some of these black holes may be in binary systems, orbiting with a companion star. These systems are the easiest to detect because the black hole pulls matter from its companion and emits X-rays. But most black holes are solitary, and they are nearly impossible to find. They drift through the galaxy, dark and unknown, their presence only revealed by the occasional gravitational lensing event or the subtle motion of nearby stars. The Milky Way itself is a dynamic place. It is not a static disk of stars, but an evolving system shaped by gravity, star formation, and mergers. Over time, the galaxy has absorbed smaller galaxies, adding their stars and gas to its own structure. These mergers have also added black holes to the Milky Way's population. Some of these black holes are ancient, remnants of the first generations of stars. Others are younger, formed from massive stars that lived and died relatively recently. The history of the Milky Way is written in its black holes. Each one is a record of a star that once shone brightly, a memory of a time when the galaxy was younger and more chaotic. The black holes are the chroniclers of the galaxy's past, silent witnesses to billions of years of change. And yet, we are still finding new black holes. Recent surveys have discovered dozens of black hole candidates, and there are likely many more waiting to be found. The next generation of telescopes will search for black holes using gravitational lensing, X-ray emission, and gravitational wave signals. We are on the verge of a new era of black hole discovery. But for tonight, we can rest in the knowledge that the black holes are out there, patient and still. They are part of the universe, and we are part of it too. We are connected to them through gravity, through the atoms that were forged in stars, through the shared history of the cosmos. The black holes are not separate from us. They are part of us, and we are part of them. Let us drift a little deeper now. Let us think about the end of the universe and the fate of black holes. If the universe continues to expand, and all evidence suggests that it will, then the galaxies will eventually drift apart. The stars will burn out. The gas will be used up, and the black holes will be the last objects to remain. Over time, the black holes will continue to evaporate through Hawking radiation. For a stellar mass black hole, this takes about 10^67 years. For a supermassive black hole, it takes even longer, up to 10^100 years or more. These are numbers so vast that they have no meaning in human terms. They are the timescales of eternity. But even the black holes will eventually disappear. When they evaporate, they release their mass back into the universe as radiation. The radiation will spread out, thinning over time, until the universe is a cold, dark void. It will be the end of the story, the final fading of the last light. And yet, even that is not truly the end. The radiation will continue to expand, perhaps forever. The universe will continue to change, even if it is cold and dark. And perhaps, in some distant future, new physics will emerge. Perhaps the vacuum will decay, creating new universes. Perhaps the cycle will begin again. We do not know. The ultimate fate of the universe is one of the great mysteries of cosmology. But we do know that black holes will play a central role in that fate. They are the dominant objects of the far future, the last remnants of the stars that once lit up the cosmos. They are the enduring symbols of the universe's long journey from light to darkness. This is a humbling thought. The universe began with light and will end with darkness. The stars are temporary. The galaxies are temporary. Even the black holes are temporary, in the longest of long views. The only constant is change. But that is also a source of comfort. The universe is not static. It is alive, evolving, transforming. We are part of that transformation. We are part of the story. Our atoms will one day be part of new stars, new planets, new life. We will be recycled, reused, reborn. The cycle continues. And in the meantime, we are here, in this moment, drifting towards sleep. The black holes are out there, patient and still, holding their secrets in the deepest darkness. But we are here, safe and warm, our hearts beating in the rhythm of life. We are part of the universe, and the universe is part of us. Let us rest now. Let us let our thoughts become light and spacious, like starlight fading at the edge of sleep. Let us release the tension in our bodies, the worries in our minds, the questions that do not need to be answered tonight. The black holes will keep their patient silence. The universe will keep its vast, orderly rhythm, and we will rest. There is one more thing to consider: the black hole at the center of our own galaxy, Sagittarius A. It is not a threat. It is not a danger. It is simply there, holding the center of the Milky Way in its gravitational grip. It is the heart of our galaxy, and it is quiet. In the future, Sagittarius A may feed on more gas and stars. It may become more active, brighter, more energetic. But that is far in the future, billions of years away. For now, it is at rest, and we are at rest too. The same is true for all the black holes in the universe. They are not rushing. They are not hungry. They are simply there, doing what they do, obeying the laws of physics. They are part of the order of the cosmos, and they are peaceful. There is a kind of comfort in this. The universe is vast and strange, but it is also orderly and predictable. The laws of physics are the same everywhere. The gravity that holds us to Earth is the same gravity that shapes black holes. We are part of the same system, governed by the same rules. We are connected to the cosmos in the most fundamental way, and that is the comfort of it. As we drift towards sleep, let us carry this thought with us. The black holes are not our enemies. They are not our destroyers. They are our teachers, our guides, our mirrors. They show us the limits of our understanding, the edge of our knowledge. They invite us to wonder, to explore, to dream. They are the deepest mystery in the universe, and they are also the most peaceful. They are darkness, but they are not empty. They are gravity, but they are not threat. They are the edge of all we know, and they are beautiful. Let us rest in that beauty. Let us let our minds drift into the patient dark. There is nothing to solve, nothing to fear, only the quiet, endless night and the gentle pull of sleep. The stars are shining, the galaxy is turning, and the black holes are waiting, patient and still, at the heart of everything. They are the silent guardians of the cosmos, the keepers of the deepest secrets. And we are here, in this moment, drifting towards sleep, safe in the vastness of the universe. Sleep well, rest deeply, let the darkness hold you softly. Good night.